Okay, good morning, everyone. How is everything going? The semester still pretty reasonable? I mean, I know it always gets busy at the end of semester. So hopefully right now everything is still good. We've been talking about network layer, so let's continue talking about network layer. We already covered this slide. I'm just bringing it up again so that we're all on the same page. Remember, the main function of routing is of the network layer is routing, which is to find the path between source and destination. And the way that the router does it is through implementing a routing algorithm that finds a path, and the routing algorithm drives a forwarding table. And the forwarding table tells the router, given an input packet with a certain destination, what output interface do I forward it to, right? And then we looked at a forwarding table here, right? And we saw that because of the hierarchical nature of IP addresses, a router just needs to store a prefix, meaning the unique prefix that identifies that range of addresses, right? So, for example, we saw that if I have this routing table with 4 entries, it captures all 2 to the power 32 destinations, right? So I have 3 ranges and a catch-all otherwise. Okay, and then the way we do it is the way that a router does it, because the addresses are hierarchical, I can just match the prefix. So the way that a router decides what interface to forward on is longest prefix match. Okay, this is where we ended last time. So let's continue from here. Okay, so the issue of datagram. So this is all in the context of we were talking about datagram networks versus virtual circuit networks, and as I mentioned to you last time, this is the same consideration that you do when you decide between circuit switching and packet switching, right? So it's just in slightly different terminology at the network layer, but it's the same exact set of considerations. So we won't dwell on it too much, okay? I mean, roughly, when you want to have guarantees, you have to do resource reservation, you have to use circuit switching, okay? Or in the network layer, we call it a virtual circuit, okay? If you want opportunistic use of resources, best effort, then we go with the datagram type of networks, and that's how the internet is designed, okay? So let's take a look at what's inside a router. Okay, so now we've sort of done a high-level intro, right? We saw stuff about IP addresses and longest prefix match. Let's get into some details. So I told you a router has to do 2 things, forwarding and routing. The routing part of it will be discussed in detail when we talk about routing algorithms. We'll talk a little bit about the forwarding part of it now. Okay, so the forwarding part of it comes into play when we look at the switching fabric inside a router. So this is a sort of a high-level view of what's happening inside a router. So the router, the heart of it is a switching fabric or switch fabric that connects inputs to outputs. Because you have an input port, a set of input ports on the left, and a set of output ports on the right, and the switch fabric connects them. The routing processor is the part of is a function that computes the routes, right, that finds this path from source to a destination, and depending on what the destination address of the packet coming in, right, there's a specific output port that the packet needs to be forwarded into. So let's look a little bit of detail at these different blocks here. Okay, so here's a sort of a detailed view of the input port. So the input port essentially implements the physical layer and the link layer. Okay, so you have the line termination, whatever physical layer processing, and the data link layer processing, right? You're doing medium access control. All that is done as part of the input port, and then there's a buffer that all the packets queue up in. So that's the third block there. So while packets are waiting to be forwarded to the correct output port, they wait in a queue. So that's very important. There's input port buffering, right? This is important because if let's say the rate at which packets are forwarded is smaller than the rate at which they arrive, what's going to happen to that buffer? It's going to fill up. And when it fills up, what's going to happen to the next packet? It's going to get dropped. Right? So now we see exactly where things get dropped. Okay, one place that they get dropped is right here, at this buffer here. We also see there's a similar thing at the output port. There's an output port buffer as well. Okay, but here's the input port. Okay, and so packets come in, because remember, they're coming from other routers. So some other router forwarded it to its output port that's connected to the input port here. Okay? So that's the input port here. We'll take a quick look at the, so the output port, maybe it's worth just getting this done. So the output port, once you pass the switch, right, there's a buffer again, right? Now this buffer, this output port buffer, is packets are now waiting to be transmitted. Okay, and again, if the link rate is smaller than the rate at which packets arrive into this buffer, packets can get dropped. So here's a second source, right, where packets can get dropped. And again, just like the input port, I said it does physical layer decoding, link layer decoding. The output port is going to do link layer encoding and physical layer encoding, okay, to transmit the packet onto the medium, right? If it's Ethernet, if it's a transmission guide, or if it's a waveguide, or if it's wireless or underwater, the physical layer will take care of interfacing to the medium. Okay, so this is the two things, right? You have the input port and the output port, and in the middle is the switch. So let's go back and talk about the switch. There's broadly 3 approaches to designing a switch, the switching fabric. Remember, the switching fabric connects input port, the input ports, to the output ports. The 3 approaches are switching by memory, switching via bus, and a crossbar switch. Okay, so we'll talk about each of these in one slide each, okay? So switching via memory is quite straightforward if you think about it. So in switching via memory, you have a shared memory space that can be addressed by both the input ports and the output ports, right? So and remember, it's the processor that's coordinating all of this, right? So for example, if a packet comes in and the input port sees that this is the destination address, it finds out where I should forward it to. It stores this information in a certain memory location, and the output port can go, when it's free, it can go read it from that memory location. Right? It's instructed by the processor to read it from that memory location and take it. Okay? And so the limitation here is the rate at which you can write and read memory. Okay? And this is the constraint. So, and if you know anything about computers, reading and writing memory takes much longer than a lot of other things on a computer. Right? So the first generation of routers did this. But it's very simple. Right? It's a very simple scheme, but it has performance issues. Okay? The second generation of routers use switching via bus. When you switch via bus, you essentially have a shared medium. It's just like Ethernet. So just like Ethernet, if 2 hosts transmit at the same time, you get a collision. Here, you don't get collisions because everything is coordinated. Right? It's orchestrated by the processors, but you're still limited by the speed. You can't make 2 transfers at the same time on the bus, right? You have to coordinate it. It's a scheduling problem. But it's much faster because you can, the bus speeds are much faster than reading and writing memory. Okay, so you can get about 32 gigabit per second type of processing. Okay, so switching via bus, probably most second generation routers are using this, and many of the new so the thing about this is that because it's a shared bus, you can only have one transfer between input and output, right? I mean, here the transmissions are from an input port to an output port, right? That's the transmission on the shared medium. But if you look at this here, so I've shown you a green, what's in green here is a transmission from port A, input port A to output port Y. If you look at this, so output port Y is busy. So clearly if, let's say C, input port C wanted to send to output port Y, it must wait. But what if input port C wants to send to output port Z? Z is not busy, right? But because it's a shared bus, it cannot transmit. A crossbar switch fixes that. A crossbar switch is like a shared bus that you can cut off in, sort of adaptively. So I can make A through Y and C to Z happen at the same time. Okay? So crossbar switch is like a set of interconnected buses that you can control the connections. Right? So for example, I can have A through Y happening at the same time as B through C. Does that make sense? Okay? So it tries to improve the switching via bus, try to make that a bit more efficient, and you can get, you can roughly double the speed. Okay? So, right? So we start off with memory, switching via memory, switching via bus, and a crossbar switch. Okay? So an interconnection network. And this is not like, I told you, broad approaches. Optimizing these things is a huge area of research. To get to 60 gigabit per second, you need to do effectively this, but you need to optimize this. Right? Does that make sense? Okay? So, like, Cisco and a lot of networking groups spend a lot of time in researching this, because the more you optimize this, the faster you can operate the router. Okay? Because right now this is, or many times this is your bottleneck. Right? It's not your input and output ports. At least it's not the speed of the input and output ports. We'll see that there's another fundamental. So if I tell you this is the problem, then you might think that there's no issue with the input and output ports. But it turns out the whole system has a fundamental limitations, which I'll talk about next. But a crossbar switch gets you up to 60 gigabit per second. We already discussed the output port. So let's talk about some issues that happen at the system level. So output port queuing is essentially when the, so this is what I said, when the link rate, the outgoing link rate is less than the arrival rate. Right? Because you know that the rate at which you can switch is clearly slower than the rate at which the total rate at which packets enter the output buffer has to be less than the total rate at which they arrive to the network, right? Because the switch cannot speed things up, okay? So you get output port queuing, so you can drop packets at the output port if the packets are coming in too fast, okay? So this is, I already discussed this. The bigger problem, the more fundamental problem I'm talking about is input port queuing. Right, so I told you that if the rate at which you forward packets across the switch fabric is slower than the arrival rate, then you get build up at the input port buffer, right? And now the question is, why might that happen? Well, we already saw some ways of speeding it up, but there's some things you cannot fundamentally change, which is if there's a request for the same output port. So for example here, let's look at the example on the left. I have 3 input ports and 3 output ports. Now, packets that are read are destined for output port 1. Let's say the one on top. So we see that input ports. So let's enumerate the ports 1, 2, 3. So I have input port 1, 2, 3 and output port 1, 2, 3. Okay. So you notice that there's a red packet at the head of the queue for input port 1 and input port 3, and they're both headed for output port 1. But clearly, they both cannot access, right? So if let's say we have some contention algorithm, right, and the algorithm decides that input port 1 wins, then the red packet at input port 3 has to wait, which means that the green packet behind it has to wait. And the green packet is meant for output port 2, but that's free. So we get something called head of line blocking. So you see, this fundamentally limits the rate at which you can switch. Okay? Now, you could try to come up with an algorithm to fix the first and second packet. Like maybe you can keep track of that. But then I can show you some problems where if the third packet is that, so it's a fundamental problem. So there are lots of research being done in how do you mitigate these kind of things and not have it affect the rate at which you can forward packets significantly. Okay? Do we understand what's going on here? Anybody have any questions? Right. This is about the level that we're going to talk about the switch. But as I said, it's a huge area of research. If you Google switch design, like you will see that people are talking about speed up. How do you deal with things like this? Design algorithms that can mitigate these kind of effects. Okay? Let's move on. Okay, so that was what's inside a router. Okay, we'll next get to IP. So we already got a flavor for IP that IP addresses have this structure, right? The structure is, many times I've said it, they're hierarchical. What we mean by that is two hosts that are geographically close to each other have IP addresses that are similar. Now clearly, so can the IP addresses be the same? If two hosts are let's say I have two computers in this LT, in EA, can the IP addresses be the same? No, but they're going to be similar, right? For example, are you connected to the wireless network? And are you? Can you tell me your IP address? Both of you? It should be 172. It's okay. Okay, are you able to find it? 172.170.169. Did you say 172.17?
We differ by the last two.
Yeah, but the first 16 bits are 172.17, right? So that's the geographical similarity. So you're in the same subnet. You're in the 172.17 subnet. Okay, does that make sense? So that's what we mean by structure of IP. Okay? Whereas if you look at your MAC addresses, they won't be related. Just let's put you on the spot. Can you find your MAC address?
It's the Ethernet.
Yeah, it's on Windows. It's the are you on Windows or Mac?
I have two. One is Wi-Fi 0 and Wi-Fi 2.
I think it doesn't matter. Just pick the one that the IP address that you gave me.
Sure. So I'll just use Wi-Fi 0.
Yeah.
So it says A0:C5:.
So A0:C5. How about you? You do IP config and look for Ether address. Do you see something called Ethernet address or physical address or MAC address? Do you see a sequence of letters and numbers separated by a colon?
The only one that is separated by colons is the IPv6.
You should have an Ethernet. You guys can't see it? Are you on Windows? Well, anyway, the point I'll help you later. Please make it a point to see me. You should understand what's there. But the point I'm making is that they won't be related to each other. Can you find yours? What's yours?
For the Wi-Fi one?
Yeah. Your MAC address.
It's B8819888.
Yeah, B8, she was A0. Right? So it's completely unrelated. So my point is MAC addresses are flat. IP addresses have a hierarchical structure. So that's what we're going to talk about now, is stuff about IP. Okay? And we're also, so basically this is about the algorithms running inside IP. IP is, you could argue it's the network layer. So here are the algorithms that run at the network layer. Okay? So here's the, so this is to illustrate how things fit together at the network layer. So the routing algorithms, which we'll discuss next, routing algorithms drive the forwarding table. and that's the network layer function. There are a few other functions that are implemented at the network layer. So you have the IP protocol. The IP protocol is about it's about the addresses and how we hand them out. There's another protocol called ICMP, Internet Control Message Protocol, and that's used to send out around control messages. So ICMP is not about finding the end-to-end path, right? But it's something that needs to be done, so it's implemented here. Just like at transport layer, we saw a few functions that were implemented but not part of end-to-end reliability. Do you remember? What functions are implemented at transport layer but are not about end-to-end reliability? Do you guys remember in the back row? Hi. The two of you. Do you remember? What function at transport layer, what's implemented at transport layer, but is not related to end-to-end reliability? It's okay to say I don't know. But do you remember? Yeah? Do you guys remember? It's a yes or no question. If you don't know, you don't have to be shy. I told you, just say I don't know. But engage so that it's, so you're part of the conversation. Yeah? Some people here? I saw somebody raise their hand here. Yeah? Sorry? Yeah. Multiplexing and demultiplexing is not about end-to-end reliability. Okay? It needs to be done. It's done at transport layer. Here, ICMP is an example. Okay? So guys, don't be yeah, it's okay. I'm not picking on on any one person specifically, but you guys are here. I'm really happy that you came. Let's converse. Okay? All right. Okay, so this is our first look at the internals of a network layer packet. So this is the header. Okay, essentially, we look at the header. Just like we did for transport layer, what we're going to do is we're going to take the header in 32-bit chunks and stack it. Okay, so across is 32 bits. And again, this is nice because things are on, either 8, 16, or 32-bit boundaries. Right, so it makes it clean. Okay, so what we see in the first 32 bits, we see what IP version I'm running, what's the header length, and that's often fixed to be 20 bytes. Okay, but it can change. There's a type of service. This tells you about whether it's like TCP or UDP. For some reason, it's here. Okay, you can get an idea of what's being encapsulated. Then you have the header length in bytes, and so that's the header length, and this length is the length of the entire datagram. Okay, the second layer, the second 32 bits are a set of fields used to do a function called fragmentation and reassembly. Right? If you remember, I told you when we talked about network layer, we saw something about maximum segment size. There's also a network layer maximum. It's called maximum transmission unit. And when your packet size, your total packet size, exceeds the maximum transmission unit, MTU, you have to break up the packet. And when you break up the packet, you have to keep track of how you broke it up. And that keeping track happens in those second set of 32 bits. So that's why I called it for fragmentation. That's the breakup. And reassembly, you've broken it up, put it back together. Okay? Then you have things like time. So in the third set of 32 bits, you have time to live. Time to live is about accounting, for example, how long this packet has been in the network, or equivalently, it's usually a counter that counts how many hops has the packet gone. The reason is if you get stuck in a routing loop, you don't want packets to be routed in a loop forever, because they will. If they're in a loop, they're never going to make it to their destination. So why might there be routing loops? It turns out that routing algorithms, finding a path, meaning running a routing algorithm, is non-trivial. Right? When we talk about routing algorithms, we'll see that. So this prevents packets from living in the network forever. At some point, if the time to live gets above, let's say 30, you drop the packets. So one thing to keep in, one thing to think about is this: what is the diameter of the internet? So maybe somebody can do some research for me. Find what is so basically what's the maximum number of hops between any two destinations? That's called the diameter of a network. So what's the diameter of the internet? Because you never want to set your time to live more than that, right? Because your route will never be longer than the diameter, right? So that gives you actually an idea of, and you will see that the diameter of the internet is surprisingly small, right? So go in, if you can figure it out, shock yourself and tell me. All right, then we have upper layer tells you so I was a bit wrong. Type of service is something else. It's about network layer service. The upper layer protocol is in the upper layer field here, and then there's a header checksum. Then you have the source. So this header checksum is very similar to the checksum that's there at link and transport layers. Okay, and it's one of our big why questions, right? Why is there a checksum at all three layers? Then you have your source IP, your destination IP, and there's some optional fields which often are not used, and then your payload, which is a TCP segment. Okay, so we see that the source and IP here are very important for routing, right? Especially the destination. I got to figure out what the next hop is. Right? If I know what the source and destination are, I get a route, and the destination tells me the next hop. Okay, any questions on this? This upper layer protocol is whether I'm using TCP or UDP. Yeah, the type of service which I said was that is actually something about the network layer service. Okay? Okay, and did somebody find out what the diameter of the internet is? Yeah?
Never exceed
90? Is that what you said? 90?
No,
19? 19? Is that what people found? Sorry? So 64. 19 seems a bit low to me. I thought it was on the order of 50 or 60. Is it 64? I mean, it's obviously changing all the time, right? But this tells you that you can have a very complex network with about 60 hops. Actually, if you think about it deeply, you realize that, yeah, that makes sense. That's not it seems low, but actually it's not. Oh.
The article I found.
It's a bogus article?
I think they referenced a bogus article.
Oh, okay. Got it, okay. To me, it's around 60 because you set this thing to around 60. Sometimes I've seen a protocol set it to on the order of 30 because you turn out most routes are not more than 30. So the average route length is about 30. The maximum is the diameter, which is about 60. So to be safe, you could put 60 there. Okay, so it's a bit counterintuitive. So it's something to really think about, that the diameter of the internet is so small, or what you think of as a small number. All right. Okay, so we'll handle. So I like to handle small problems first, and then put them to bed and not think about them again. Okay, so because routing is the big function. So and actually the IP addresses and subnets are quite important. So we'll talk about fragmentation and reassembly, then talk about IP addresses and subnets, and then routing. Okay, so that's the plan. All right, here, so as I mentioned, so we saw that, or if you look at the word internet, inter means between, right? Like international, between nations, right? And intra means within. So intranet is within an organization. So the internet is between networks. So the internet is huge. It's a whole bunch of networks stitched together. Now, these kind of, we'll see later, these sub-networks are called autonomous systems. They're owned by different organizations who can set policy. And one of the policy things you can set is the maximum transmission unit. Right? So I may start off with a packet of size 1500. I transmit it and it's moving along fine. But then I'm going to enter an autonomous system for which the maximum transmission unit is 400 for whatever reason. It's an autonomous system. Even though it's part of the internet is a bunch of autonomous systems stitched together. So, but I have to follow the rules of that autonomous system. The routers on that system will drop any packet more than 400 of size 400 bytes, let's say. So IP includes a mechanism for breaking up packets, for fragmentation and reassembly. And that's what this function is. So an intermediate router may have a different policy. So we see a mother packet here. So I call this big packet the mother packet or the parent packet here. So this is the payload and this is the header. This router is going to break it up into 3 smaller packets, each with their own header, right? Because the protocol says every datagram has a header. Okay, and then at the other side you're going to reassemble them because the application needs this whole thing, right? Because we're connecting eventually 2 applications, right? So the fragmentation and reassembly is the housekeeping, right? Keeping track of how you broke it up. It's best done through an example. Okay, so we'll just do an example here. So let's say I have a 4,000 byte datagram. That's the total size. It's 20 bytes of header and 3,980 bytes of payload. Okay, this is the mother packet. And let's say the MTU for the follow-on network is 1,500 bytes. So what the fragmentation and reassembly do, it would take this very large packet and it would create multiple smaller packets, each of them less than or equal to 1,500 bytes. Okay, obviously I want to limit the number of packets I fragment into, so hopefully I try to get as many that are exactly 1,500 bytes. Right, so I minimize the total number of fragmented packets. So now since I'm assuming a 20 byte header, so that means the largest a packet can be the MTU is 1,500, so what's the largest payload? If I have a 1,500 byte packet and 20 bytes are header, what's the largest payload? What's the largest payload? You see, I get very concerned when we have a very simple question and I get no answers. Like, I would like you guys to just tell me and we move on. Yeah, I understand. Come, you need to work with me. I tried to make it clear to begin. I want you to interact, not just sit there and absorb. So you guys tell me, what's the maximum size of the payload? Can you tell me? Yeah. Okay, it's fine. I have. Suppose I tell you, you can have packets of total size 1,500 bytes. Now 20 bytes of that must be header. The rest of it is payload. So what's the biggest payload size I can have? Yeah, 1,500 minus 20, right? So you good? So my children packets will have maximum payload size of 1480 and 20 bytes of header because they have to be constrained by 1,500. So that's what I did here. I created, there's a packet here, right? This packet is of length 1,500. This packet is of length 1,500. Now the question is, what's the size of this packet? So, well, how much payload did I have to begin with? I had so maybe the gentleman in green, you work with me. We have a 4,000 byte packet originally, 20 bytes of header. How much payload is there? Yeah, which is what? Yeah, 3980. So I need to make sure that 3980, all that payload ends up as payload in my 3 mother packets, right? So I have, in the first packet, first child packet, I have 1480. Second child packet, I have 1480. How much is left? 1480 plus 1480, and take that and subtract that from what? 3980. And what's left? So what's 3980 minus? Yeah, it's 1020. So this third packet is of size 1040 because it needs its own 20 byte header. Right? So do these numbers make sense? There's nothing, I'm serious, it's nothing but housekeeping. Okay? Now what you need to do, there's one more thing. So this makes 3 packets that now meet the MTU requirements, the 1500 byte size requirement. What I need to do, I need a little bit more of housekeeping. How am I going to stitch these together again? Right? I need to say where these, because remember, once these three leave, they can all take different paths. Because the internet is best effort. They're not guaranteed to arrive in order, right? They all take different routers. In fact, some might even get dropped. Okay, so you need to find a way to connect them back together. And so you need to keep track of how they fit together. The way we do that is through an offset flag. Okay, we say, where does this fit? So the first packet, which is the beginning, is at offset 0. The second one has an offset, and the third one has an offset. So, forget about the numbers I have. Tell me the offset in bytes for the second packet. Where does the second packet fit after the first packet? A bit louder? Yeah, the offset should be 1480 bytes, right? Because it's the second packet. And what should the offset of the third packet be? 2 times 1480, right? So that's in bytes. And if you can understand that, you're done. That's it. Okay, and there's a fragment flag to say this is part of a fragment. Okay, these are fragments. I need an offset, right? And the length is done, so I meet the requirement. So the number of packets, I have to make sure all my payload is somewhere in there. If you can get that, that's it. That's fragmentation and reassembly. Okay, so don't worry about the numbers in the offset yet. Just know that you need an offset to stitch it back together. Okay, so can I check? Anybody have a question? Are we good with that? Yeah. Oh, I need to know that, like I'm done, because I don't know initially how big the packet was. So this tells me that, like, because there's an ID. So notice there's an ID. So all these belong to the same mother packet, and once I get 0, I know I'm done. Does that make sense? So I collect all the ones that have fragment flag 1, and then I get 0. Okay, I know I got them all. Yeah, that's a good question. Okay, so if we get that, let's do just one tiny thing for efficiency. Instead of the offset being in bytes, because if the offset is in bytes, the number of bits needed, what's the number of bits you need to represent, let's say, 0 through 1024? You need 10. You need basically log base 2 of the range, right? Because 2 to the 10 is 1024, right? So if the offset is in bytes, yeah, I'll need a certain number of bits depending on how big the offsets are. But if I want to reduce the number of bits, right, that I need for the offset field, you can do that by saying, okay, I'm not going to represent the offset in bytes, but maybe I'll represent it in like 8-byte chunks. Right? If I represent it in 8-byte chunks, you need a smaller range, right? And so you need less bits. So what IP does is actually, this is in 8-byte chunks. So that means you can only break on 8-byte boundaries. You can't break, arbitrarily on arbitrary byte. But this is okay. This restriction turns out to be not so bad, right? You might end up with, in a very small case, an extra packet because you didn't fill up the rest, right? Okay, depending on the relationship between the MTU and the actual packet size, you might end up with an extra packet, but it's okay. All right, so that's why this offset, if you notice, the offset field, instead of being 1480, I did it as 1480 divided by 8. Okay, so does that make sense? I'm allowing you to break only in 8-byte chunks. So you can't break at every byte. 8-byte, I can break on 8-byte boundaries. So that means my offset is in 8 bytes. Okay, and that's why these numbers. So these numbers are a bit smaller, right? 185 is smaller. It's an order of magnitude smaller than 1480. So you can imagine you need less bits to represent the offset field. Any questions? Yeah. Yeah, but remember, it doesn't. It is. It's pretty consistent. I cannot say that you cannot implement something else. You can, because you control the routers. So you can change it. Yeah, you have a question?
Why was 8 chosen? Why not 16?
Yeah, because the bigger you make the constraint, the less, the higher probability you might not fill up the entire space and end up with an extra packet. Right? The way to get minimum number of packets is to break on byte boundaries. Then you can always fill up. You have 20 byte header. Like if I give you, if I told you your constraint was, instead of 1500 bytes, told you it was 1400 bytes, then you can only have 1380 payload, and 1380, if you divide it based on your packet size, may end up with an extra. If you only are on 8-bit chunks, you might end up with an extra packet. If you make it 16-bit, you might end up with an extra packet. So it's right. You want to fill up your children packet as much as possible. Whereas if you're on large chunk boundaries, you may not be able to fill it up. Does that make sense? So even though your offset number of bits needed is smaller, you might waste space. Does that help? Yeah?
Is it possible to do reassembly if the divisor is too small from router or like network to network? Because they might be
The reconstruction only happens at the end. It only happens at the end destination. You don't reconstruct at an intermediate point.
Let's say if my offset is divided by 16, then I'll have more fragmented packet tray just at my subnet. And then when it goes to the other subnet, when it's divided by 8, then I'll have to sort of like.
What do you mean it's not divided by 8 anymore? Once they're broken up, they're done, right? So this is the idea. Let's go back here. So at an intermediate node, they are broken up because maybe the follow-on network has a constraint on the MTU. So this big mother packet is broken up. Now for the rest of the network, these 3 packets just act on their own. They act independently. If for whatever reason they have to be broken up again, then it's like nested. Does that make sense? Yeah.
So if one of those intermediate packets are dropped, and there's a timeout, for example, and the sender, it sends the whole big packets.
Yeah, you're right, exactly. TCP has to kick in, yeah.
Yeah, and then it's
Yes, absolutely.
2 fragments again.
Yes, because network layer is not end-to-end. Absolutely right. If one of these packets gets dropped, then TCP has to kick in. And that whole mother packet has to be resent. Yeah. This is primarily because networks are owned by different ISPs who can impose their own policy. This will come up again when we talk about BGP, Border Gateway Protocol, which is balancing routing, efficiency of routing with policy issues. This is like a policy issue, right? But it affects the technical part. Okay, so that's it. So we wrapped up IP addressing. So the next thing we're going to talk about, I'm mindful of the time, so we'll just briefly start it. We're going to talk about IP addressing. We've already said that an IP address is 32 bits, right? We break it up into 32 bits into what 8-bit chunks. Each 8-bit chunk we convert to decimal, right? To an unsigned decimal. So when Chenhui said her IP address was 172 dot something, we call that decimal dotted notation. But it represents these 32 bits. Okay? The other thing I want you to keep note of is that every network interface has an IP address. So is that clear? A network interface has an IP address. Okay? And this is an example. I have a core router with 3 network interfaces. And these 3 network interfaces, each of them define a subnet, okay? And if you look at the IP addresses of all the nodes on the 3 subnets, you'll see that they all have a common part. That's called the network part. So you see, for example, at the bottom, they're all 223.1.3, right? the first 24 bits are the same. That's the network part. Then you have .1, .2, .27. That's the host part. Okay? So IP addresses are like this. I already said that the way you define a subnet is by a network interface. So every network interface defines a new subnet. Right? So in this case, I have 3 subnets. Okay? So in the example that I gave you, I'm going to just, I think, so as I told you, there's a network part. So this tells me that the first 20, so the subnet mask encodes how many bits in the network part. So this tells me that there's 24 bits in the network part, which is consistent because the ones down here had the first 24 bits the same. That was the network part. Okay, I'm going to leave you with just one thing, which is in this network, how many subnets are there? Okay, so think about it and let me know if you have questions. Just come up. Okay, when we come back next time, we'll continue talking about IP addressing, and we'll talk about NAT and routing. Okay, but remember, there's no class on Monday. Do you know why? It's a holiday. It's the observation of Diwali. Okay, or here it's in the South India they call it Deepavali. The North we call it Diwali. It's on Sunday, but it's observed on Monday. Okay, so no class on Monday, but we meet on Wednesday. Okay, and for those of you who are here, thank you. Please make sure you come on Wednesday. Okay, we're going to do something interesting. And those of you in webcast, hello, please come on next Wednesday. Okay, thank you. Remember, I want you to think how many subnets in this diagram here. Thank you.